How many unique paths are there from the top left to the bottom right of an n by n grid, given you can only move down or to the right from each cell? In this video, I'm going to solve this problem using a method I introduced in the previous video, which is to start with a recursive solution, which might have exponential running time, and then introduce a cache to speed up the running time, and then convert that to a bottom-up solution in which you're not making any recursive calls, you're just iteratively building up a cache, and then from that point to then make some space-saving adjustments to that cache. So if any of this stuff isn't familiar with you, just check out the previous video in the series. I'm going to put a link to the playlist in the description. And so to get started with this video, or for this problem, let's print out this grid. This is just a helper function to print out the grid. And so let's take a look at it. And so the question is, how many ways are there to get from up here all the way down here if from each cell you can only go down or to the right? And the key for this type of problem is to think backwards. So to think from the final cell that you want to reach, you can only have possibly come from above or from the left. So if you know the number of ways to get here and the number of ways to get here, you just add those together, and that's the solution for the problem. And then you can apply that same method to this subproblem and then also this subproblem, and it continues on like that. And what makes this a dynamic programming problem instead of just a recursive problem is the fact that there's these overlapping subproblems. So we can reach this cell both from making a recursive call up here that then goes left, or from left and then right. And it's the same thing with all these cells. There's multiple paths that we can reach there. And so what we're going to do is once we have a basic recursive solution, we're going to introduce caching, so we only actually solve each subproblem once. And so let's get started on the recursive solution. So let's introduce some functions for the problem. We'll use paths for the main problem, the number of unique ways. And we need some inputs for some test cases. Okay, and so when we call this, it should log the output of 28. And let's get started on the recursive solution. So we're going to have to add the values of the cell above and the cell to the left. So that'll be m minus 1, that's going to be the row above, and the same value of n, because we're on the same column, and the same row and the column to the left. And then for the base case, it'll just be if we're in the first row or the first column. So if m is equal to 1, or if n is equal to 1, we'll just return 1. And let's call this and see if it returns 28. And it does, so it's working. And now one thing we can show is that if we make these numbers a lot bigger, that the function just won't return. And we can do the same trick that we did before. We're just to prove this, we'll just log an incrementing value, so we can see that we're just making a billion different recursive calls. So let's introduce caching to get a runtime improvement. And I think what we're going to do is we're going to create the cache here, and then we're going to pass it into a helper function, which is going to do the actual recursive logic, and then we're going to return the value directly out of the cache. So let's create the cache. It's going to be an array. And it's going to be m plus 1 because we want to be able to index into the mth value. And in JavaScript you have to use this fill function in order to map over the values. And from each row we're going to have to make another array because we're making a matrix, and that's just going to be n plus 1. And I guess we can initialize everything with the value of 0. So let's just print this out to make sure that that it's actually of the right size and stuff. And I guess we have to make it smaller first. So this should be a 4 by 8 grid of zeros. Okay, it looks like we're calling something else here. so we don't need this. Let's test that again. Okay, so there it is. It's a 4 by 8. So we have our cache initialized. So we're done this step. We can get rid of these debugging statements. And now what we have to do is call the helper function that's actually going to kick off the recursion. So we're basically just going to copy over the logic from the basic recursive function, except we're also going to take the cache. So it's going to take m&n and dp, and let's just copy this old logic over. And then in addition, actually first let's fix these function calls. That's a pretty common mistake actually. If you don't update that kind of thing, you can end up in some confusing situations. We also have to pass in dp. Okay, and then we also have to insert the value into the cache instead of just returning it. So let's say, let's come up with some good names for these things. This one's the row above, so we'll say from above for this call. And this one's going to be from the left. And then we'll just insert this into the cache for the m and n value. And it's the number of ways from above plus the number of ways from the left. And then we're going to return the value directly out of the cache again. And one thing we still have to do is check from the top here so we don't continue recursing if we've already solved the problem. So we'll check if the value exists in the cache for these arguments. We're just going to return it. And then we also have to actually make the call. So it'll be m&n and passing in the cache. So let's call this, and this should return 28. And actually, let's try and look at the cache after we're done. Okay, and it actually worked. To convert this into a bottom-up solution, we're just going to concentrate on the cache. And the first thing I think we should do is let's get rid of this the recursive code, because we're not going to need that. And what we're going to do is we're going to concern ourselves with the I guess the way the cache looks before we start, because we're going to need those base cases in before we start iterating through the cache, inserting the values. So so let's add this back in so we can print it out first. And what we want to have is the first row and the first column all filled with ones, because the only way to reach those cells are either from the cell directly above or directly to the left. And since it's the first row, it's only going to have one way to get there. So I guess let's just add basic iterator. And using this off by one thing's a little tricky, so it's going to be the first value. So in all the first columns for all the rows, we're going to assign to 1. And we're going to do the same thing, but now reaching into the columns instead of the rows. So we'll just switch these values. Let's take a look at this. Oops, that's way too big. Let's reduce this back to 3 and 7. Okay, and so basically what we're going to do is, now that we have these 1 values in here, and remember this stuff up here doesn't matter, we should never be touching it. So we could have started at 1 instead of 0, but it doesn't matter. And now what we're going to do is we're going to iterate starting here, and we're just going to look at the value to the top and the value to the left. And then once we reach this cell, we're going to have just filled this in. And then we can do this whole row, and then by the time we're here, we're going to have this whole row filled in, and we can just continue on and do the whole thing. And so let's do that. And so what we're going to do is we're going to have to loop through all the I and j values within this within the cache, starting at 2, because we have 1 and 1 already filled in. So this will be starting at row 2, as long as it's less than the length. And we're going to have to do the same thing for j, so that's going to be for the columns starting at 2. And have to just reach into the first row just to get the size of the thing. We could also use m and n, but we're just duplicating it. And all we have to do is set the I and j value equal to the row above, the result from the row above, plus the column to the left. So that's just going to be j minus 1. And since we're starting at 2, we're never going to run out of values. And this should fill in the whole thing. And we'll just print it out too to make sure. And remember, this is still not, okay, so this did work, but we are still using m by n space. So at this point we have a working bottom-up solution. And one thing we can do to bring down the space requirement is to basically start overwriting previous parts in the cache that we don't need anymore. And so let me just print this out again. So basically, you can imagine if we were inputting this value 15, we only have to reference value 5 and 10 in the cache, and everything above we don't need anymore. And that means we can kind of wrap around and then start up here, and then we can continue on. This is the same thing I did with the staircase example, except now we're doing it with full rows instead of individual values in a single array. But the concept's the same. And I think it's easiest to see this first with just 2 rows, because we only need the previous row. And so whenever we're working on inputting values, we'll write to a new row, and then as soon as we go to the next one, we'll just wrap back around. So we need only 2 rows. And to do that, I guess we'll restrict the size of this just down to 2. And then I need to be a little careful with this, because we still have to go through the entire m values, not just 2, which is the length of the DP now. So let's input m here. And then all we have to do is whenever we index into the cache, we're just going to use mod 2, and that'll just guarantee that we wrap around and only write into values of 0 and 1 into the array. And again, I always like doing this only after having an actual working implementation. I think it's a lot harder to debug if you're trying to do this the first time around. And let's see if this actually worked. And there we go. We have now we're only using 2 rows, and the value's the same. So let's just do one more just to check that this worked, that it's actually wrapping around. And it is. You can see the 0 row has higher values than the row before, because it's actually dependent on that. So this value 84 came from the left, from 56 plus 28, and that's 84. So at this point we have, this is actually constant, actually it's not a constant space, it's I guess a constant times, it's 2 times n plus 1 space. But and it's m by n time, because we still have to visit all the values from 0 up to m by n. Just improving on this further, there's actually one more optimization we can make, which is we can actually decrease this from 2 rows to just a single row. And so let's take another look at this. And basically the idea is that from each cell, because we only have to look up and to the left, what we can do is just reuse a single array, and then instead of copying this value above into a new row, we'll just overwrite the value that's already there. And we can do that because we're never going to have to reference it again. And for the most part, I actually don't really like solutions like this, at least when you're trying to solve a problem, because it's kind of hard to debug. Like if we were at this index here and we were printing out the thing and looking at it, you would have to be aware that everything to the left is from the current row, and everything to the right would still be from the previous row. And so it's a little bit harder with debugging, but the final solutions are shorter and nicer, and I guess they do use a little bit less memory. So let's convert this to just a a single row for the DP. So we're just going to use the columns now. So say DP equals this, and we have to be careful with the base cases, because for the entire first row, remember the values are all 1. So let's fill this with 1. And then we don't need this anymore because that was just initializing the values that we just did with by using .fill1. And we do still need the 2 loops because we're going to have to do m iterations through the array. And let's just change this to n just so in case something goes wrong I can figure it out. And now what we have to do, I'm just going to delete this, is let's see, I guess we'll use j because we're looking at a column, and I guess we're actually not even going to use this outer value I at all. And it's just going to be the current values. This would be essentially what was the row above, and then we'll have to also add to the left, which is just going to be j-1, the column to the left. And that is a very quick, easy looking thing. And I guess what do we return? I guess we return will be just the nth value, and we'll know that we've already gone through m iterations, so we don't have to worry about m anymore. And let's just print this out just to look at it. And I think this should work. Let's see. So I think this should print out just this first row here. Okay, and it worked. So at this point, this is the optimal solution. And hopefully from watching this video, if you just opened up the solution and looked at this, I can imagine that being kind of confusing, but hopefully you can see that if you start from the recursive solution, introduce caching, think about the cache, build up the cache iteratively, and then start thinking about reducing the space, you could arrive at this on your own.